Welcome, everyone. Today we'll be discussing hierarchical cluster analysis, a fundamental technique in unsupervised data mining. Let's get started. In this three-part chapter, we learn how to conduct clustering analysis and association analysis. Unsupervised data mining differs from supervised methods, as it requires no knowledge of the target variable. The algorithms are designed to identify complex processes and patterns without analyst guidance. This makes it an essential part of exploratory data analysis. We will explore two core techniques, cluster analysis and association rule analysis. These methods rely on similarity measures like Euclidean, Manhattan, and Jacquard's coefficients to uncover patterns in the data. Cluster analysis is an unsupervised technique that groups data based on shared characteristics. Observations within a cluster are similar to one another but dissimilar to those in other clusters. This method is valuable for summarizing large data sets into a smaller number of meaningful groups, providing a foundation for understanding the characteristics of each cluster. Often, this technique is used before supervised learning to organize observations with distinct patterns. The two main clustering techniques we will focus on are hierarchical clustering and k-means clustering. Hierarchical clustering groups data into a hierarchy of clusters through an iterative process. There are two approaches. Agglomerative clustering, AGNES, which is bottom-up, starts with each observation as its own cluster and merges similar clusters iteratively. Divisive clustering, DIANA, which is top-down, begins with a single cluster and separates the most dissimilar observations in each step. For this lecture, we will concentrate on agglomerative clustering, which is the more commonly used method. It can handle numerical, categorical, and mixed variables. AGNES begins by treating each observation as its own cluster. Clusters are merged iteratively based on similarity until one final cluster called the root remains. For numerical variables, similarity is measured using Euclidean or Manhattan distances, while categorical variables use Jacquard's or matching coefficients. Numerical data is standardized using z-scores to ensure comparability. The algorithm also calculates distances between observations and clusters or between two clusters. To evaluate similarity between clusters, the algorithm uses various linkage methods. Single linkage, nearest distance between observations in different clusters. Complete linkage, farthest distance between observations in different clusters. Centroid linkage, distance between cluster centroids. Average linkage, average distance between all pairs of observations in different clusters. Ward's method uses the error sum of squares, ESS, to minimize information loss when merging clusters. Once the clustering process is complete, the results are represented as a dendrogram, a tree-like structure where branches represent clusters and leaves represent individual observations. The height of the branches indicates dissimilarity between clusters. Analysts can visually inspect the dendrogram and determine the appropriate number of clusters by cutting it at the desired level. Large distances between merged subclusters suggest distinct groupings. On this slide, we have a dendrogram. The number of clusters is represented by branches on the x-axis. The distance between clusters is represented by the height indicated on the y-axis. Relying solely on dendrogram height may yield clusters that are statistically distinct but lack practical significance. To address this, we combine quantitative measures like dendrograms with practical considerations and descriptive statistics. Additionally, we can incorporate variables not used in clustering, but relevant for profiling the clusters. The effectiveness of clustering depends on how well the algorithm, distance measures, and data transformations are chosen. Testing multiple techniques is often necessary. Using the cities file, we can create clusters of cities based on crime rate, poverty rate, and median income. Hierarchical clustering helps identify groups of cities with similar socioeconomic profiles, guiding decisions in fields like urban planning or policy development. The methods and considerations we've discussed can be applied in this context to ensure meaningful and actionable results. Let's build the example using JASP. First, select Hierarchical Clustering under the Machine Learning tab. Next, we will replicate the settings and variable modeling as depicted on this slide. Move the variables of crime, poverty, and income into the variables box. Then choose the appropriated options for tables and parameters. The results provide information on the number of members for each cluster, and we can see standardized means for the variables in each cluster. To see the actual mean values for each cluster, we will need to select the Descriptives tab. Drag the input variables as depicted on this slide. Then drag the cluster variable into the split box. Make the appropriate selections under the Statistics drop-down as shown here. Now we can see the mean value of each variable within each cluster. We use this information to help build descriptions of the cluster for comparison and contrast with other clusters. For example, Cluster 1 has the highest average income and the lowest average poverty when compared against clusters 2 and 3. Now, let's talk about analyzing mixed data, data sets that include both numerical and categorical variables, which are common in business applications. To handle mixed data, we use Gower's coefficient, a similarity measure proposed by John Gower. Gower's coefficient scales all variables to a range between 0 and 1, ensuring comparability between numerical and categorical features. It then calculates a weighted average of the scaled distances to measure similarity between observations. This approach is particularly useful for clustering data sets with diverse variable types, making it highly relevant for applications like customer segmentation or market analysis. To conclude, hierarchical clustering is a powerful exploratory tool in unsupervised data mining. Its data-driven approach and intuitive dendrogram visualization make it especially useful for identifying patterns and relationships in small to medium-sized data sets. While its limitations, such as scalability and sensitivity to data changes, pose challenges, it remains a valuable first step in many clustering analyses. In practical scenarios, combining hierarchical clustering with other methods can help overcome its weaknesses and enhance its applicability to larger datasets or more complex problems. Always consider the context of your analysis, the nature of your data, and the specific insights you aim to derive when choosing clustering techniques. This wraps up our discussion on hierarchical clustering. Thank you for your attention.